Hello and welcome back. So we stopped right here last time when we tested our statistician class. Super fun, exciting stuff. And now we're going to talk about constructors, because again we're still trying to come up with classes on our own. And we had one final issue at the very end, if you remember. We had that init function that was always required to be called on a statistician right after you made it, for it to set up all the necessary member variables to their initial values. Well, we can do better with that. We can do better than that. We can use this thing called a constructor. So my example is going to be using this idea of a counter, very simple little class. It mimics this like thing that, I don't know, you use when you're counting how many times you jump rope or something. Maybe it's used at track meets. I don't remember exactly where it's used, but I think athletics likes this a lot. For example, if we make a counter class, we'll keep track of like the number that it's represented on this little dial. So we'll have like an init function to start out at 0, a reset function also to put it to 0 for a different reason. Then we'll have like an increment button or function that mimics pressing this little button on the counter. And you can imagine that you need one of these in your program to like keep track of how much you suck at Wii bowling. Like I would need this to track how many times you get the ball in the gutter, for example. Or like, I don't know, what's your current high score? What's your current score in the game if your score only increments by 1 each time? So let's make this counter class and give it an init function and then fix that init function. Make it a constructor. Okay? So I think you're noticing that I like to do a lot of little examples in the class, and remember that you get all this from me. Alright, so I'm in my CSCI 41 folder. I'll make a folder for today. Go inside of it, and let's make a folder called counter. I don't know if we'll need any more than this, but I'm just getting ready. So vim counter.cvp. So we're going to make our class. It's going to be called counter. And it's going to model this thing. So it's going to have a private member variable, because we know what private means now, and it's useful, that keeps track of the current count on this counter. And for our public methods, we will have that init function that starts it out. We will have an increment function. And we'll have a reset function. And you know, we'll also need to get that count back because it's currently private. We'll have a getter. Int get count. Alright, that looks good to me. And let's see, gotta have that semicolon, of course. And we can implement all this stuff. We can say void counter init. Implement it. Do the same for increment, reset. Essentially the same thing for like get count. Yes, but of course this needs to now be int counter. All right, so now we'll go and implement these. So init needs to set the count to be 0. Reset will do the same thing, but init is only ever called once, at the very start. You'll do the same thing. You'll add 1 to the count. So this is like pressing the button. And then if the user ever wants to see the current count, we will definitely give it to the user, but we'll make them pass through this public getter function or method. So we'll return our count. Right? Done, done, done. Now, yeah, I think that's fine. And then we'll have a main function that includes our stuff and like uses it. So handy dandy return 0, and then we'll make a counter. Counter c dot init. Gotta always start it out at 0. Then we'll say c.inc, and one more for good measure, and then we'll print it out. Yeah. And I forgot to include IOStream and use namespace standard. I'm putting this in a weird spot for reasons. This is all well and good, but again, we learned how to split our stuff up. So let's make a counter.h. Put the declaration. We'll make a main.cpp. Boop. There we go. We'll include counter.h, which is that. We'll make sure to not ever have any infinite inclusion. And then we will customarily, well, we're required to at this point because it's a class, we'll include counter.h so that this thing knows which class it's implementing. It needs to find this counter namespace, which is made with the definition of the class. And it found it. Okay. Now we're set. This might be complaining for no good reason, and I think it is. If I make one change to this file, are you going to be happy? No. Let's make sure that I saved counter.h just in case, but I think it's alright. So this is just complaining for no good reason. Oops. Now, I gotta get into my folders. I'm gonna say, to compile, G++, count all my C++ files. Counter.cpp, main.cpp, and I'll call it main again. Cool. And if you can guess, of course, the count is now going to be 3 after we do this. Let's test reset. And maybe we'll only do it 2 times now. So we should see 3 then 2. Beautiful. Alright, so that's our counter. And, oh, that was a fun little key combination. Wouldn't it be nice and get rid of this bad boy? Because it's error prone. Like, you always have to remember to call it. It's no fun having to remember to call this. We're all about fun in this class. So we're going to use a constructor. And a constructor is a special function that gets called right after an object is born. Doesn't matter if it was born on the stack, born on the heap. Does not matter. It just always gets called. It's a function with the same name as the class, and no return type because it doesn't make sense. It's like you're making that class. There is no need for a return type. And so it's a great place to initialize your stuff. So we're going to get rid of our init function, and we're going to make our own. So we're going to make a special kind of constructor, which is called a default constructor. It's one that requires no arguments whatsoever. So it's going to be like this, counter. That's the name of it. No return type. Okay, this is our constructor. If I could spell. So now that we have it, let's implement it. And honestly, we couldn't have a harder job if we tried. So, an easier job if we tried. That's it. So this is our constructor implementation. There we go. And it's guaranteed to always happen when we use it. So no need for this anymore. The constructor is called implicitly here. And it's called a default constructor because it required no arguments. It's like you did this, you know? So there was no need. And default constructors are quite nice, especially when you're using like vectors and things. So let's see, do I want to get into that? Sure. It's possible to have a non-default constructor, of course, which is a constructor that takes an argument. And we're going to get rid of an it. We could have it take an initial value. So instead of 0, we could have whatever the user asks for. Yeah? And this will still work, so long as we always remember to call it. So now we're forced to give an argument to our constructor. It's no longer a default constructor. All right. So let's go ahead and compile and run this. Just make sure it's all still working. Sure. And I have a few more tricks up my sleeve. So let's get rid of this. 0 should be like the normal default. So I can turn this parameterized constructor into a default constructor by providing a default argument. So it has that default argument, and it'll just get applied with that if you don't provide one. Okay, so you can have the best of both worlds, really. And so that's nice. So what we just made was a default constructor in a special way. Now, I'm telling you that constructors always get called for you, no matter what, implicitly or explicitly if you do it yourself. And you might be yelling at me through the screen, and feel free to do that most days. But right now, I was not lying. Even though we had that init function, there was secretly a default constructor that was made for us. Okay? We didn't make it, the compiler put it in for us. And what it does is it calls the default constructors of all the member variables in the order that they're declared. And that might be a lot to take in right now. We're going to go over that in more detail later. Not in this lecture. All right? So even if we didn't have one would be made for us, and it would call the default constructors of all of our member variables. But right now we only have primitive type member variables, so it doesn't really do anything. But if we had like a vector, then it would call the constructor for that vector, which would initialize it to be empty. That's what a vector does when it's initialized. That's what its constructor does. Okay? Well, I'm good with that now. I'm learning how to ruin that screen. Yeah, so the default constructor, which is interesting. That'll come up later. Now, one nice thing, it's a bit of a shortcut, and it's quite useful, is to use something called an initializer list. So inside of your constructor, here's the class called blah's constructor. If that's not obvious, let me draw it. So that's blah's constructor. And now, what's happening is I have an empty body, but I'm still initializing variables. So pretend that blorg and blarg were both member variables of blah, the blah class. So let's call those, make sure that those are member vars. And this is constructor style initialization, in a sense. It's happening before the body happens, because it's textually there and also necessary. So you can have an empty body and initialize the variables still if you use this thing called an initializer list, which is a colon after your arguments. And the way to remember how to do this is to remember this little sad face. Okay? So that is an initializer list. And so we can initialize our counter. We can set the count to be the initial value, just like this. We can use an initializer list. We can get rid of this and be like, count, no. Pretend int was a class and call its constructor. Count is initial value, please. Okay? So that is us using an initializer list to set count to initial value. And I'm going to want that all on the same line, so let's do that and join that and capitalize. Oh, no, not capitalize that. Capitalize that. Okay, so it's as if you did this line right here. Count equals initial value. And the reason this works, even though count is an int, it's not really a class, this is called constructor style initialization. So let me go to the main function and show you this. All right, so int x equals 42 is equivalent to the following. Pretend I also used x. I'm not allowed to for the compiler's sake. But pretend y was x, and I did this. This also sets y to be 42. Yeah, so you can do this for any type, including primitive types like int, which aren't really a class in C++. All right, so initializer lists are super nice, and they are a way to initialize things. And they're especially useful when your class is made up of classes. So again, let's pretend we had this vector. This vector, if you don't put anything in the initializer list to call its constructor, well then, it's too late in the body. If you wanted to, like, for example, do like the following in main, so vector int blah, give it an initial size of 42, you'd have to call the constructor on the vector in the initializer list, just like this. All right? So you'd have to say blah 42. So you call the vector's constructor in the initializer list to make sure that it does what you want. And yeah, looks like it didn't save that. And also, I guess I'll include this for you, because why not? I was considering just deleting it, but we'll keep it. So now it should be happy. Dun dun dun. It's not complaining for a real reason. It should just work still. We're not using blah, of course. But that's the idea. That's what it's for. Now, I think that's what I wanted to say about that. Initializer lists. They're the only way to call a constructor on a member variable that is a class type. All right? And remember that sad face. And now moving on to const member functions. So const is nice because it keeps people from changing your stuff. It can be up, any variable that you have can be up converted into a const. So for example, you really trust a function that takes one of your variables as a const reference, for example, because you're guaranteed that because it's treating it like a const, it can never change it. So you can also apply const to your own functions inside of a class. So because it's your function, it's kind of guaranteeing that you won't mess with your stuff, which is exactly kind of what you want. It makes sure that your member functions, if you mark it as const, it's ensuring that you can't modify your own variables. And that's great because you should never trust yourself as a programmer. So they're kind of like little sanity checks for you. So example. Any function that changes something cannot be const. So inc changes count, changes a member variable, can't be const. Reset changes count, can't be const. Get count, though, can be. So the way to mark a function, mark a method as const, is you put it after the declaration, but before the body. Constructors can never be const either. All right, so this is our one case of a const function, and you got to mark it in both places. All getters should be const. Okay, because it's not changing anything. And the reason this is a sanity check is because it prevents you from having to write a million little tests like this. It prevents you from doing the following, so you never have to check whether or not you did the following. I can't say something like count equals -42. Oops. Back, please. All right. So the compiler is gonna say, you cannot assign a const member function. You can't not assign a member variable inside of a const member function. All right, which is beautiful. That's exactly what we want to see. This is keeping us from doing this. All right, and this is still fine. Yay. So I hope that makes sense. Const is super useful. It keeps you from ruining things. Yeah. All my little key combinations are going all over the place, aren't they? So before we move on to operator overloading, which is really fun, 2 more slides here. So pointers to classes is something you might not be familiar with. So let's talk about that. Let's pretend I, in main, want to not just have my counter C, I want to have a pointer to that. So I'll say counter star C2 maybe. I can give it the address of C. And so now I have a pointer to my counter C. Yeah? Now, I could also make it on the heap as well, a brand new counter. Just like that, or you can call a constructor with a different default value, but that's quite possible. This I don't want to really get into right now. This is just fine. So now we've made our counter C lives on the stack, and counter C2 points to C. And it's counter star. What does this mean? Oops. Well, C is my normal counter, yeah? And because it's a counter, it has the count inside of it. It's a little box in memory. Stores its stuff. That doesn't really look like the word count. Let me fix that. There we go. And I think it held 2 at the time that we made this pointer. And now C2, well, it's not a counter. It is a pointer to a counter. Counter star. Which means it doesn't have a little count inside of it. You can't say C2 dot get count, for example. This does not work. Not allowed, because the dot implies that you are a counter, and you are not if you are a counter pointer. So really, this box of memory that is C2 holds the memory address of C, which, for example, let's say it lives at address 100 in memory. So C2 would hold 100, and then it would be pointing to C if you were to draw the diagram like this. Yeah? So instead of saying C2.getCount, you have to dereference C2 to get to the actual counter that has member variables and member functions and methods, you know? So you have to say star C2. Then you can say .getCount. Then it would work. Okay? And then everybody decided that this is ugly because of the precedence rules for the dereference operator, you actually have to you are required to use these parentheses, and that's just way too much typing, too many shifts. So people have made an equivalent way of doing things, which is beautiful. And so I will represent beauty with a rainbow. This is equivalent to the following shorthand. C2 arrow, which is dash greater than get count. Those are equivalent things, and people really prefer that arrow. It both dereferences and applies the dot to something. All right? So if you ever have pointers, remember the arrow. So if I want to, in order to call get count on C2, you must do either C2 dereference, put in parentheses, dot get count, or C2 arrow get count. All right, so that's what you do when you have pointers to work with. Okay, that's the fun. And then finally, just a little summary slide of all the things that we've been talking about and learned. things that you should always keep in mind. So you should always make your member variables private because you want to limit access to who gets to modify your stuff. You should be the one to modify your things. And you'll write getters and setters as necessary. So getters get your member variables in a special way. Setters can set your member variables in a special way if you want to give access. So for example, maybe you can make a setter that allows you to set count, but you don't trust the user. So we'll do void set count int new count. Perhaps you don't trust the user and you always want your counter to uphold the invariant that the count is never negative. So if the user tries to set count to be negative, and if you made it public, you could not prevent this. But because it's private and we're using a setter, we can. So if new count, what the user wanted to set it to is less than 0, well, screw you, user. We're going to set the count to 0. Otherwise, we'll do what the user intended. This lets us prevent things that we don't want to happen. Alright, so they're allowed to set the count, but only to the values we want them to set it to. Okay? And the same for the getter. You can make special getters that get the members in a special way. Okay? Maybe that member didn't even exist. You made your own getter for something that you have to build. That's all possible. So yeah, write constructors instead of those silly init functions. Excuse me. And make sure to initialize all your member variables, because if you remember from CSCI 40, your count, if you start it out, if you say new class, new counter, or counter C, and you make a new object called of type counter, and you don't initialize count anywhere in the constructor somewhere else, well, count is going to be undefined, yeah? And that'll never be what you want, so make sure to always initialize your stuff and restrict access to your users because you don't trust them, ever, ever, ever. So make as few functions as possible public, make as many functions as possible const. Let's see, is there anything else? Yeah, the setter has to be non-const. And then pass around const references to save copies from getting made. So every time you pass a reference, it's essentially passing a pointer that's harder to screw up instead of copying the whole thing. And we'll talk in depth about this kind of copying that we don't like in a future lecture. And then make sure to test all your stuff. I gave you some examples of that last time, and I'm going to force you to make some tests in your lab. Okay? So now, the last things, let's talk about operator overloading. So let's make a plus operator to combine two counters. So if we go back to, I don't know, the Wii bowling example, pretend that you had a counter that represented one game where you sucked and you had like 3 gutter balls, and then you had another game where you did slightly better and you had 2 gutter balls, but now you have 2 counters all over the place. Wouldn't it be nice if you could add those together and see how badly you can play Wii bowling in total? So if we had a plus operator to combine the counters, we could do that. So let's see here. Let me show you what we want. Let me make another counter. I'll call it do I want to I'll just keep that. I'll call it C3. Why not? And I will increment it 3 times. Because why not? And so now C2, remember we reset it, so it has 2, and C3 has 3. So if I could do something like this, counter C4 equals C2, C1, it's C, plus C3, should have count equal to the counts of both of them. So 2 plus 3, 5. Wouldn't it be nice if we could make a plus operator that didn't work for like ints or doubles, but for counters, for classes? And yes, we can. We can do that. So that's really nice. Let me actually I'm going to move some comments around. So that comment can go there, and what we're about to do is write a function that is the plus operator. So this gets turned into, by the compiler, the following. C dot operator plus called with C3. All right, so we're gonna write a member function on counter that is called operator plus. So that's it. In operator, like plus, like minus, like times, like less than, it's secretly a function. It looks like this, operator op. It's the name, where op is like the thing. Operator plus, the plus sign would go here instead of op. Okay? And that's weird, but it works. So you can make it inside the class or outside the class. And so we're going to make this one inside the class, and I'll show you what that means. That means that C is the first thing, and then C3 is the second thing, and it's its one argument. So the operator plus function is a member function that is called on the object C with the second thing to add it. Okay? And we're going to return a brand new counter. So that might all sound really weird, but I'm going to give an example, and hopefully it makes sense. So this is a Ooh, I do not know what happened there, but everything froze. Hopefully you can still hear me. Sorry about that. It looks like it's still recording. We will see later if it's still going. But yeah, the idea is what we want to do is write a member function called operator plus. So plus operator. We'll go here, and so we'll say void. Or no, sorry, counter. It returns a counter. Operator plus. Sorry, my computer freezing tripped me up a bit. And then it'll take a const counter reference, because we don't want to pass things around that are weird, and that's the other counter. All right, so the idea is this takes our current counter object and adds other into adds others count with our own, and makes a brand new counter with that. So that's essentially what it means to add things, right? And you can make your own version of this, and you could do random things, but this makes the most sense, I think. So this is the plus operation on counters. So what it's going to do is it's going to make a brand new counter, counter result, and results count will be equal to our current count, because this is a member function, plus others count. And that's how that's going to work. And it's complaining to me right now because this is a member function. And that's why it gets to access the private member variables. And oops, I spelled that wrong. And then we have to return result. So now you see exactly how this plus operation is going to work in main. It's going to take C. It's going to take C3. And it's going to call C dot operator plus with C3. And it'll add those two counters together. And then we can say C4's count, maybe. The combined count. We'll call get count. And so this, because of the way we did it, C held 2 at the time, and C3 holds 3 because 3 increments. So C4's dot get count, now if we implemented our plus operator correctly, should return 5. Hey, very nice, very nice. All right, so that was a operator called plus that lived inside the class. All right, so let's make a times operator now that lives outside the class. All right, and it's going to need to be a friend because we need to access that count private member variable. But let's get started. So it's going to be very similar, but not. Actually, I'll go to the main function. So let's make counter C5. Oops. C5 C5's count. Sorry, I keep doing that. Let's say it's C4 times C3. Why not? And because this one, we're going to make it outside of the class. It's not a member function, so there's no dot involved. It's going to be called operator times. And the way we gave it is the first thing was C4, the second thing was C3. So this is how it will look. Right? It's just a normal function called operator star. C4, C3 are its two parameters. It's two arguments in this case. And then we'll output its count, C5.getCount, which should be, let's see, 5 times 3, so 15. So that's what we want. Let's make this member function. And oops, that looks really ugly because of the way I put the comment. So let's make it pretty again. Okay, back to counter.h. So we're going to make this outside of any class. Returns a counter still. It's operator star. And it takes 2 arguments this time, one for each side of the star. Because it's not defined inside of a class. It needs both of them. All right. It's not implicitly working on one like the member function operator plus was. So now I'll take both. Const counter reference x, we'll say const counter reference y. And so we'll do the same thing. No, sorry. This is the header file. How dare I try to implement something? Down here we'll implement it. We'll make our counter result. And this one's result.count. Actually, I could just copy most of this, can't I? We'll change that to be star. And this is not going to work because that's x.count times y.count. This won't work because these are member variables that are private of counter, and we do not have access to those at the moment. So, how do we get them? We need to become a friend. Yay. So we'll say, this guy, I know him. He is my friend. Give him access to my private member variables, please. Now, this should be happy. And everything should be wonderful. It compiles, it's still complaining because it only remembers the old stuff for some reason. But now it's saying C5's count is 15. Beautiful. So now we made that star operator, which is awesome. And then every operator that you can think of, you can make your own. Okay? And it can do random things. You can make the star operator just print out an infinite loop of hellos, if you would really like that. And you can look up in the documentation any of these. So these are all your options. You can do like, you can even override the assignment operator. What? Relational things, which return bools in that case. Less than or equal to, not equal to. You got your pluses, your times, your modulo. All these things you can override. Make your own. And we're about to do this one. Okay. So with that, that brings us to the output operator. Now, what this is a way to give a custom output to cout of a certain class that you make. So, for example, that was a lot of words and I think I jumbled them. So let's pretend we had our counter and we wanted to print that. Wouldn't it be nice if we could just say, sorry, count on my brain, if we just said cout C, where C was a counter. Right now, if we do this to the compiler, it's going to be like, dude, what are you trying to do? It will say all this stuff. It has no clue how to make it something that is printable. But we know how to overload operators So we can make our own version of this left shift operator, these two little arrows. And the way it works is, well, cout has to go first. Actually, let me show you why these types make sense. Alright, so O stream is the type of cout. If you look it up, that's what it is. Now you know. Cout's type is O stream. And then your type goes here. It's going to be this thing on the second. It's going to be the thing on the right-hand side of this cout operation. Okay? So, the reason it makes sense like this is because, actually let me, first of all, erase the end L. That would make more sense. The reason it looks like this is because it's the output operator being first applied to cout and then applied to your class C. Okay? So that's why you give it the type of cout, then you give it the type of your thing. And then you might be wondering, why do we give it back a reference to the type of cout? Well, the reason for that is so that we can chain. We give back cout itself. In order to chain output cout calls. So it allows you to do something like this: cout, C, and then a new line. Because thanks to the precedence rules of this operator, this left shift two less than sign operators, the parentheses will get drawn like this. It'll do this one first, and then this will return something. This whole computation will return something, and the idea is it needs to return cout. If it returns cout again, it's as if it's just saying it first prints out C and then it turns it into cout end line. And you can do this with as many things on the same line. So that's how you keep giving things to cout. You secretly, in the operator, return cout every time you print something. Okay? So in order to make ours work like that, we have to give it this type. Okay? So now, let's do this. We don't actually need to make this a friend, I don't think, because we have our get count. Okay. What we can do is, well, I would like to, if I can, copy all of this, because gosh, is that a lot. Yeah. Yeah. Oh no, sorry, no, I'm in the terminal, it's not really gonna work, is it? So it's OStream, reference, operator, that, left shift, OStream reference, OS, and then usually you'll give it a const reference to your thing. Okay, and so the idea is always return cout, or OS, at the end, and implement this as if OS was cout. That is, give it stuff with that operator on other types. Okay? So let's pretend every time we give our counter to cout, we want it to say the following. I don't know, current count. And then we'll give c.getCount. All right? And maybe a new line. Yeah? And so that's the idea. We pretend that OS, because we will be getting cout as the OS parameter. That will be, our argument is cout in this case. And we'll print to cout. It's just a new variable, a new name for it. The current count, then the count, which is just an int. It already knows how to do that built in. And then a new line. Okay? So it's complaining right now to me because I did not include IOStream in this file. And this is also going to become an issue in counter.h, so let's just let counter.h include that as well. Or instead. Alright, so now it's happy. If only I gave it Oh no, did I put the declaration in a weird place? Or did I not give one at all? I must have not given one at all. There we go. Sorry about that. Declare our function. And because this is in .h, this is standard OStream. Standard OStream. This should be happy. This should now be happy. And yeah, I think now in main, we can say coutc and have it not complain to us. So let's see if the terminal is happy with this. And it is. Hey, and what it does is it prints C5's count, new line, then it prints current count 2, and then a new line. And then because our own output operator outputted a new line, it outputted an extra one. So maybe in ours we don't need that new line, do we? So now it'll print without that extra new line at the very end. Okay, so this is how we make our own output operators for our own type. So remember that the type of cout is OStream. And so that's why we take 1 as the first parameter, because when we call cout something, cout's the first thing that this operator sees. Okay? And just an aside, this will also work for files. So if you had like an OF stream, it also has this operator, and an OF stream just so happens to also be an OStream for reasons that will only become apparent at the very end of this class, I think. So that'll work. And then you can do the same thing with the flipped operator, with the input operator on cin or IF streams by changing OStream to iStream. I'm not going to make you do that in this class, I don't think, but now you know your options. Okay, so that brings us to the end of these slides. And at the very end, I want to give you a few exercises to think about, and maybe pause and try and answer them yourselves. So at a minimum, how many test cases do you think you should need for this vague piece of code? Now, assuming you've paused and thought about this, well, I think the answer should be, well, there's one way to get into this if statement's body. There's another way to get to this else if statement's body, probably. And then there's a third way to get to this else statement's final body. All right, and only one of these can ever be executed on a certain input. Well, we should have at least 3 different test cases that get us to each of these places. Because then we can make sure that it does the right thing here, it does the right thing here, it does the right thing here, and it won't surprise us. So I say that 3 is the correct answer. Okay? And then for this one, which of these 2 programs, pretend you made them, will take longer as n gets very large? Okay, gets close to infinity, let's say. A function that adds n numbers, so for example, 1 plus 2 plus 3 all the way to n. You're going to need a loop to do that, right? Or drawing a box of stars of width n. So if n was 3, this is a 3 by 3 box. Yeah? N. You'll also need a loop to do this one. Okay, so what do you think will take longer? And the idea is, well, how much work are you really doing in each of these programs? It comes down to, if you could just like unwind all of the operations that you do without using loops, really the things that matter for the summing n numbers are all these pluses. You're going to do n minus 1 pluses. And for this one, you're going to do n times n. Cout star, yeah? So now, knowing that, which one do you think will take longer? I say B. Okay? So this is the kind of stuff I want to get you to start thinking about in the back of your mind. Your book will make this more concrete. I will make this more concrete in future lectures. But I really want to start you thinking about this kind of stuff. All right? And then finally, this is something that I'll have you do some more research on your own, I think. But be able to for example, on a test, explain the difference between a struct and a class in C++ as you know it. If you want to go down the rabbit hole, there is more to the difference between a struct and a class in C++. And the hint, if you want to look this up, a struct can actually have member functions, in fact, which is the weirdest thing to think about. But normally though, we never use a struct for that. That is weird. But you can, okay? Normally in this class, we'll think of a struct as something that holds a bunch of types, and that should really be your main answer here, okay? But if you want to look into this, please do so. And yeah, this brings us to the end of our first slide. If any of this stuff from this first week has been confusing, luckily you can re-watch the video, look at all of the code that I've written, and if things are still horrible, please come to office hours and yell at me. Like, this isn't making sense, fix that. Fix this in my mind, please. And I'll give you as many examples as I need to give, okay? I'm happy and happy to interact with humans because it's so weird to talk to myself right now. I know I say a lot, but yeah, thank you for getting through this first week of lectures with me. I will be back in your lab introduction video, so look forward to that, and I will see you then.